So this is our second example of curve sketching. And by looking at this function, y equals x squared minus 4 over x squared minus 2, we first want to recognize that this is a rational function. It's a polynomial divided by another polynomial. And there could be a domain issue. Not all the time in a rational function, but we have to think about the fact that there are times when the denominator may be equal to 0. And so if we set the denominator equal to 0, it tells us that we're going to have an issue when x is equal to plus or minus the square root of 2. So it tells us that our domain is going to be everything, because anything else is going to be okay, that x cannot be plus or minus the square root of 2. And that'll come back in a minute, but it does tell us something about the domain. When we move on to intercepts, we think about the y-intercept. We let x equal 0. And if we do that, you can see that if we let x equal 0, we're going to have negative 4 over negative 2, which is 2. So x equals 0, y equals negative 4 divided by negative 2, which is 2. So we get the point 0, 2. In terms of x-intercepts, that's when the function itself is equal to 0. So we're thinking about what happens in this case. And we know from earlier things we've talked about that the only way that this can be equal to 0 is if the numerator is equal to 0, which tells us this, which tells us this. So x is plus or minus 2 would give us 0. So that tells us that we have an intercept at 2, 0, and negative 2, 0. So we have some different points, so you want to go ahead and put those onto your graph that you have at the bottom of the page so that you already know that those 3 points exist, 0, 2, 2, 0, and negative 2, 0. When we think about symmetry, let's think about what would happen if we plugged in a negative x to our function. We know it's not periodic. That's just something we know about rational functions. But if we plug in negative x, you can see that we're going to have x squared minus 4, or maybe I should put it here, x squared minus 4, and the denominator x squared minus 2. So that's because both of those pieces are squared. So when we do that, we can see, well, we're going to end up with the same exact thing. And we know from earlier work we've done in the course that when you have the same exact thing, when you plug in negative x, this function is therefore even and has symmetry over the y-axis. So we have that for our symmetry, and that just tells us something, so that when we're graphing this, if we don't have symmetry over the y-axis, if we don't have the same thing on the left-hand side and the right-hand side of the y-axis, we've got an issue. With asymptotes, we should think about our vertical asymptotes we've already figured out because I don't need the S there. Vertical asymptotes. Due to our domain, we can see that x equaling the square root of 2 and x equaling negative root 2 are going to be asymptotes. They're going to be vertical lines that our function will never be able to touch. In terms of horizontal asymptotes, we know that we will have them because we have a rational function, and we learned this when we talked about limits to infinity. We will not have a slant or a oblique asymptote because the degrees are the same. So from the work that we did in earlier sections, if we think about the limit as x goes to infinity of x squared minus 4 over x squared minus 2, and we were to divide the top and bottom of this function by the highest degree of the denominator, it would look like this, the term with the highest degree in the denominator. It's going to look like this, and that would be the limit as x approaches infinity of 1 minus 4 over x squared over 1 minus 2 over x squared. And yeah, you do have to kind of show me this. If this is a possibility, why is it what you think it's going to be? And by doing this and saying, okay, as x goes to infinity, this goes to 0. As x goes to infinity, here this goes to 0. We can see that we get 1. And really what that tells us from that section on limits is that now we have a horizontal asymptote at y equals 1. And we could do the same thing with negative infinity, and because this is even, we're going to do the same thing. We're going to approach y equals 1. So there's our horizontal asymptotes. And again, no slant or oblique asymptotes here. So you can, on your graph, you can draw your vertical asymptotes going at, you know, square root of 2 is like 1.41. So you got 1.41, you got a line there. You got negative 1.41, you got a line there. And then you even have a line, so I'm doing kind of a dotted line here at those 3 spots. So y equals 1, and then your 2 vertical asymptotes. And by doing that and putting on your points, you're already in like really good shape for what this graph looks like. So I've already given you the first and second derivatives here. This is just to make life, you know, a little bit easier in terms of, you know, what we care about, which is just like, what does it mean that we now have this? And you're welcome to use the quotient rule and make sure that you can get this derivative, but I am assuming at this point that you can do a quotient rule and find the first and second derivatives. So we have our first derivative, and of course what we care about is when is this equal to 0 and when is it undefined. And so this function is going to be equal to 0 when the numerator is equal to 0. So that gives us the value of x equals 0. So I care about that value. And then the other values that I care about are what would make the derivative undefined. And that would be when the denominator is 0. And we can see that that would be when the denominator is 0, which of course we already know is when this inside is equal to 0, which we already know from other work that we've done, that that's going to be plus or minus square root 2. So I'm going to put those values on as well. So I'm going to put x equals negative root 2, and over here I'm going to put x equals the square root of 2. And I can, if I want, even think about doing something like this to just remind me that these are my vertical asymptotes here. And then we simply plug in values on all parts of these intervals to see if our function's increasing or decreasing and where it's increasing or decreasing. So notice on the first derivative, the denominator is always going to be positive. So really all we care about is what's happening with x in the numerator. And so when you plug in something less than negative root 2, so just pick like negative 100, your derivative is going to be negative in the numerator, but it's going to be positive in the denominator. So that's going to give us a negative. And even if we pick something between negative root 2 and 0, like negative 1, the numerator is still going to be negative, denominator is always going to be positive, so you're going to have this. And then if you pick something between 0 and root 2, like 1, you're going to now have a positive over a positive, and then anything greater than root 2, like 100, is going to give you a positive over a positive. So we can pretty quickly create our chart here, and we can see that we're going to be decreasing on any point less than 0, and we're going to be increasing any point greater than 0. And we don't want to forget that that does tell us that our function's, you know, decreasing and then increasing. And so this should be a local min right here. And we can put this back in. So if you put 0 back into the original function, you already know that you're going to have 2. So y equals 2. And so you're going to have 0, 2. And so besides being a y-intercept, that's going to be a local min. So so that does tell us stuff. So we know stuff already. Now the last thing we would need would be any changes in concavity. And what you can see with this is that if we were to think about when what we have could be equal to 0, it would be the same thing. We'd set the numerator equal to 0, but that's the same as finding out when this is equal to 0. And you can kind of go as far as you want in this, but it's pretty clear to see that it's not going to be possible. You're not going to be able to have x squared equaling a negative 2 over 3 with a real number. And so what that tells us is simply that there's no place where the derivative is equal to 0. However, in terms of a concavity, you still want to think about when and if I'm saying derivative, I'm sorry, second derivative, we also still have to think about when it's undefined. And that's the same values that we had before, because our denominator, and you fast forward through this part if you totally understand it, but all we want to think about is x squared minus 2 is equal to 0. And again, it's just these plus or minus the root 2. So we still want to check what's happening on either side of those. So I'm going to go like this, just to remind myself. Okay, so all that really tells us that the only place that the concavity would even change, these are not points of inflection, but any place where it could change would just be on any sides of these intervals. So we plug, and again we're plugging this now into our second derivative. We plug in like a negative 100. The numerator is always going to be, as you can see, always going to be negative, and the denominator will be the only thing that could change. So if we put in negative 100, numerator is negative, denominator is going to be positive, so that's going to tell us that we are concave down. If we put in something between negative root 2 and root 2 into the original, we put in like 0. Again, we're always going to have negative in the numerator, and that denominator at this point is going to be negative. So negative over negative is positive, and then say we put in something like 100, anything greater than root 2. And if we put in like 100, we're going to get a numerator that is negative and a denominator that is positive. So that's going to give us negative. So it tells us that we're concave down, and then we're concave up, and then we're concave down. So I'd like it if you would put all those things together onto your graph, see if you can get the graph of this, knowing all of these things, and then go ahead and graph it. And you should end up with this. So notice that we have, so I'll just kind of use the red here to remind you what these things look like. So we have those vertical asymptotes at the root 2. So I have a hard time on the tablet here, but we have like root 2, negative root 2, and root 2 is our asymptotes here. Oh my gosh. Yay. All right, we also have the horizontal asymptote of 1. So that's what's happening here. And then what you can see is that, like we said, we were concave down all the way up until negative root 2. Then we were concave up between negative root 2 and root 2. Notice we have our local min at 0, 2. So that's that point right here. And that is the only local min or local max we have. And then after the square root of 2, we're concave down again. So notice that we're concave down. Notice that we are approaching our vertical asymptotes, we're approaching our horizontal asymptotes, things that we need from pre-calculus, not even calculus. And we also found that notice we're decreasing up until negative root 2. Then we're also decreasing from the other side of negative root 2 down to 0. And then after that, we're increasing continuously. But of course, we have those vertical asymptotes that do break things up a little bit, so we have to pay attention to that. But we are decreasing, this is decreasing, here we're decreasing, then on the other side we're increasing, and then we're also increasing over here. So those were those values we got from the first derivative. So altogether, this is what this graph looks like.